Hi everyone, welcome to today's Learn and Share. We're excited to have Jens presenting his paper, Do You Need Zero Knowledge Proof? Jens is from TU Munich. He has worked on blockchain and DeFi for a while. He has worked on quite a few different subjects, such as censorship, attacks, benchmarks. I think we had actually a talk or discussed about ZK bench not that long ago. Jens worked on it. This is a paper from Jens. I'm really sorry if I pronounce it very badly. Ernstberger, Stefanos Kaliasos, Lee Jo, Filip Jovanovic, and Arthur Jarve. So thanks, Jens, for coming here, and we're very excited with this interactive session.
Perfect. Thank you, Raphael. Great. Yeah, today I'm going to present the work that's called Do You Need a Zero Knowledge Proof? And kind of the motivation behind all of this was there's a lot of focus on snarks at the moment, essentially in industry and due to their popularity in blockchains. So this is kind of an attempt at giving kind of high-level guidance for non-experts or people kind of joining the field to kind of like broaden a bit the perspective on what is actually possible and why certain protocols are used in some contexts and not in others. Right. So what I'm going to talk about today is essentially first the solution space of zero-knowledge proofs. So what kind of zero-knowledge proofs or different approaches to zero-knowledge proofs exist on a fairly high level, and what are their different performance trade-offs. Then we'll dive into a specific example, which is TLS oracles. So quickly, for you that don't know what TLS oracles are, essentially how you have to think about it is the following. So assume you have TLS, right? Like TLS secures all connections on the internet. So you have a client and a server, and all of it is kind of like encrypted via this transport layer security protocol. What TLS oracles allow you is basically proving that some data originated from a server to like a third party, right? So how you have to think about is this basically you have like normal oracles like from Chainlink, and these prove basically consistency about like some public API, right? Like for example, weather data or something. By having like an Oracle network, everybody can access the API and comes to an agreement. With TLS oracles, you can access private data. So if I'm the only one having access to an API endpoint, you can use a TLS oracle to prove correctness of the data that you obtained from any server. And what's really interesting here is that there's kind of a bunch of different approaches to this, to solving this problem with different kind of security properties and also performance properties. So we'll talk about that, and then I'll give like an overview of some other ZKP applications, what kind of like zero knowledge proof they use. And finally, we'll talk a bit about whether you actually need a zero knowledge proof in some applications or not. Okay, great. So for the kind of solution space, so what we do in the paper is basically we give like a non-exhaustive overview, like fairly broad, about different solutions, that being Sigma protocols, commit and proof protocols, MPC in the head, and also snarks. Snarks is probably the kind of broad spectrum of solutions that all of you are most familiar with. A snark basically has the properties that it's non-interactive. It has very, very small proof, a very computationally intensive verifier, and very little communication. Whereas you have a fairly computationally expensive prover, right? For commit and proof protocols, these are also commonly called interactive proof protocols, I guess, or dedicated verifier proofs. So the thing here is you have a verifier, and the verifier basically keeps a secret value that is relevant for the completion of the protocol. So it's inherently private coin. So you can't apply the fiat heuristic. And the downside is a little bit that you have like a larger proof size, and you have communication that is more than one round due to the inherent interactivity of the protocol when you're basically going over the full circuit. But what you get is basically a very performant prover with also a low memory overhead. Another class of protocols is basically MPC in the head. So what this does is you let the prover essentially emulate a bunch of virtual servers in its head, right? And then afterwards, you commit to the individual views of each virtual server in the protocol, and let the verifier challenge basically a bunch of these views of the individually simulated servers. Yeah, then you basically obtain zero knowledge due to the privacy properties of MPC. You get a protocol that is fairly similar to the commit then proof approach, but also like with a large proof size and an even larger communication. To give you like a rough guideline, like I think the most recent one is like 2x communication, as opposed to kind of like the commit then proof protocol approach. Yeah, and then finally you have Sigma protocols. Sigma protocols, essentially how that works is you have like a verifier and a prover, right? Where the name comes from is you have like a commitment phase, then you have a challenge phase, then you send the proof, and then you send the verification result, and that result's kind of like in a Sigma kind of ladder. So that's why they're called Sigma protocols. The interesting part here is that you can also obtain non-interactivity with the Fiat-Shamir heuristic. You have little communication, albeit not as little as in the case of Snarks, because your proof size is kind of larger. And kind of downside is you have a prover and a verifier that are both linear in the statement size. So naively, you might think, so why don't we use Snarks for everything, right? So let me quickly give you an intuition about this, based on like a practical example from the identity space. Probably some of you are familiar with kind of like some of this. So essentially, if you want to have like privacy preserving identity proofs, what you usually do is you have like a holder of the credential, and the holder has a bunch of attributes. So for example, like name, nickname, address, date of birth, and ID number, right? Then what you want to do is you want to present this credential to some kind of verifier, right? Like, I don't know, some government entity, but you want to preserve your privacy and therefore only disclose a subset of attributes, and also like you want to prove like certain predicates on these attributes, right? Yeah, so this is kind of like the problem statement that is roughly solved ideally with Sigma protocols. So how this is done, basically you first have to issue the credential, right? And this is essentially done by using blind signatures. So here you have like an overview of what is being done in the verifiable credential community and like for the standard of decentralized identity. So essentially you use BBS plus signatures. BBS plus signatures were conceived, I think, like roughly 10 to 15 years ago now. So there's a long line of work that initially started in the space to obtain privacy preserving credentials. Also like in the early 2010s, late 2000s, there was already like practical systems from IBM, for example. It's called EDMX, that leveraged like similar principles, right? And so the latest kind of proposal makes use of BBS plus credentials, which use BBS plus signatures due to kind of like their advantages, performance properties, as opposed to other kind of like signature schemes. And how that basically works is you have like a key generation algorithm, where the key generation algorithm gives you like a secret key and a public key. So this is commonly run by the issuer, right? So you need to run key generation. Then you basically sign the attributes or messages from the holder, right? So what you do is the holder sends kind of like the messages, which are kind of like the attributes of all of this, to the issuer, and the issuer issues a signature over kind of like the individual attributes, right? And then afterwards, what you can do is you take the signature and you verify this. The signature is essentially a credential, including your attributes, right? So you get a signature. You send this back to the holder, And then you basically present the credential to the verifier, and the verifier can verify basically a signature. And the interesting property of these protocols is that you can selectively disclose attributes without revealing the signature. So why is that beneficial? Because if you would present the signature to the verifier, you could trivially, like, if the issuer and the verifier are both government entities, so it's kind of like the same entity, you would be able kind of like to link the issuance to the verification, right? So this is like the property of unlinkability. There's some extensions that like make the whole thing blind, so you also can issue without disclosing the attributes in the first place. And so the interesting part where the zero knowledge proof part comes in the presentation of the credential is that you use a Sigma protocol on top of kind of like the signature scheme to only reveal a selective number of attributes and also not reveal the signature, right? So how this works is essentially you give the signature. This is from another paper, but it's like roughly the same signature, same signature and proof of knowledge scheme. So you receive the signature and the commitment to the messages, and then you basically let the verifier pick a random challenge. So as I said before, right, Sigma protocol, you have like the commit, the challenge, and then kind of like the response period. And based on kind of like the challenge that you send, the approver responds with some variables, and afterwards the verifier can check basically the two pairings are equal, and then compute this statement. And based on that, like, I'm not going to go into like any more details than that, but based on that, you can basically verify that like the attributes that are committed to or that are revealed are assigned by the issuer without revealing the actual signature. So what's interesting about this is that you have to perform a number of group operations that is linear in the size of the number of statements that are previously issued by the issuer, right, for the credential. And also the proof size is dependent on that. So, right, so you might come up with two questions at this point, right? Which is, why don't we use snarks for identity? This is possible. There have been previous approaches to this where you use snarks specifically for obtaining similar properties of unlinkability, anonymity, blind issuance, and stuff, and then basically verifying them on a blockchain. So there have been academic works on that. But specifically, this is used in the proposal for decentralized identity because you have like a different setting, right? So you have like the blockchain, right? And the blockchain, what it essentially does, the only thing it stores is from the issuer, you store the public key, and then the verifier can kind of fetch the public key from the blockchain, right? So it kind of like in this sense, you don't do any credential verification on chain. So you really don't need a snark for this application that is envisioned in the decentralized identity specification. Right, because you only use basically a ledger as a public registry for public keys, so everybody can fetch their public keys without directly talking to the issuer. Right. So that is the benefit in this case. And the other question is, why don't we use Sigma protocols for generic NP statements, right? So theoretically, what you could do is you could express any generic NP relation as a combination of algebraic statements. So as a combination of kind of like discrete logarithm relations or something, right? Where you express each gate in the circuit, in an arithmetic circuit, as a relation between the input and the output wires, but as algebraic relations, right? But if you then apply like a Sigma protocol like this one to it, then you're going to inherently have like a very costly prover and verifier, because both of them run linear in the size of the statement or linear in the size of the messages, right? So in this case, you have several exponentiations per gate, which can basically also get an intuition from this protocol, where you basically have the commitment to the message vector, and the longer the message, the more you have to kind of compute. Okay, to give you a better intuition of this is how it works in practice. So this is the actual numbers of like measuring this. So you can see basically the proof size is basically a number of bytes that is linear in the number of hidden messages. And if you want to create a proof and you basically scale the number of messages while only revealing one of them, you can already see that the time basically linearly increases with the number of messages in the proof that you want to prove for, right? So that's why you basically don't use Sigma protocols for any generic NP relations. Right. So what we can get from that is basically that you have to consider different things when choosing your zero knowledge proof protocol based on the application that you want to apply it to, right? So basically the performance is very dependent on the nature of the proven statement. So if you have like a statement that is very trivially describable by some kind of algebraic relation, it might be better to use a Sigma protocol and basically, yeah, exploit the performance properties here. But then you have to kind of like struggle with like the proof and the verifier being linear in the size of the statement. Whereas, for example, for non-algebraic structures, like for example, some kind of hash is the SHA-256, some kind of hash is the SHA-256 of some pre-image, or some kind of ciphertext is the AES encryption of some plain text. It would be more efficient to use Boolean circuits. And also for non-algebraic structures like SHA-256 and AES-128, it's also not as inexpensive in snarks per se. So here, commit and proof protocols would be better because you would have to basically operate with non-native arithmetic in snarks, because you need to basically emulate existing algorithms in the fields that you operate in like, let's say, like a pairing-based snark. So what you would like to have ideally, right, is like the best of all worlds. So and that is exactly why we're going to talk about TLS oracles, because here it's very interesting. You kind of operate on algorithms that are conceived without thinking about zero knowledge proofs, but you still kind of want to verify some of these things on chain. So you kind of like need to think about this to combine different kind of zero knowledge protocols to come up with like a very optimal solution, I guess, right? Okay, so TLS oracles. So what you have in TLS, you have a server, you have a client. So what you operate usually is this protocol, right? So this is TLS 1.3. And you can already see, like, you have a bunch of HKDFs, which is a hash-based key derivation function. Usually you have two invocations for of SHA-256 in each of those. And you can see that that kind of like, yeah, is quite a bit if you want to prove the handshake in a TLS session to like a third party. And then afterwards you have the record layer where you use AES or some kind of other authenticated encryption scheme that allows you to prove kind of like that a plain text is encrypted by a specific key that you derived previously in the TLS session. So, right. So for TLS, what you do is you have a client, you have a server. The client knows the secret key of the client and the secret key of the server, and the server also knows the secret key of the client and the secret key of the server, right? This is because we have symmetric keys, and requests are always encrypted with the client secret key, and responses are always encrypted with the server secret key. This is a bit oversimplified, but it kind of like gets the message across for what we want to say. So you might say like the client might trivially prove that some kind of data that it obtained from a server is correct, right? So you might want to say, okay, we have a verifier and I just create a proof that, like, I don't know, AES encryption holds. This is not going to work because you know the client knows this key, so it can basically encrypt arbitrary data under that key and prove like correct encryption to the verifier without the verifier being able to verify that it's actually authentic. Right. So you need some kind of other solution for that. And the solution that like was initially conceived like a couple of years ago, I think this already started like 10 years ago even, but it is basically to emulate the client in two-party computation, right? So what you actually want is a commitment from the client to the ciphertext that you obtain from the server, that commitment that can be obtained by the verifier without the client being able to change what is committed to, right? So in order to achieve that, what you do is you emulate the fault client in 2PC, and first of all, you compute kind of the shared key, the secret keys of the TLS session in 2PC, where the client itself only holds a part of the secret key and the verifier holds the other part, both for client secret key and the server side secret key. Then you compute the request in 2PC, basically because like none of them can compute individually because the keys are shared. And you send that request to the server. Here it's important that like the server, you can't change the server because otherwise you would have to change like every single server to support this kind of like TLS Oracle protocol on the whole web. So you don't get really legacy compatibility. So that's why you kind of like encrypt this request in 2PC, and then you receive the response. Now the interesting part is the client here can't decrypt the response at this point in time after receiving it, because it only holds a part of the key, right, not the full key. So what it does is it commits to the response, and then afterwards the verifier reveals the secret key, and then the client can basically compute a proof that something is encrypted under the secret key, right? Like that I decrypted and encrypted correctly, and then you just use a CK snark, right? So this is like the initial kind of solution that was conceived for this problem. Now you might observe that, for example, the verifier can be computationally powerful, right? We're not operating in any blockchain environment here. We can just like run the verifier on any obtainable server, and it can be fairly powerful. And also it can be designated. So as you already see here in 2PC, you kind of like split the keys, right? So the verifier already holds a secret itself, and you can only execute this protocol with this single verifier. So there's no one else that you can execute it anyways. So why not use a different zero knowledge proof protocol that makes use of this kind of assumption anyways, right? Yeah, the second thing is you have in-circuit AES encryption, right? Because here you decrypt with the secret key, and then you need to basically prove correct encryption. This is also prohibitively expensive because, as I mentioned before, if you want to basically work on non-algebraic structures and snarks like AES or SHA-256, you need to perform the AES encryption with emulated arithmetic, which is non-native to the field that you're operating on, and therefore it's also very expensive. So it incurs like a lot of numbers of constraints in like R1CS or whatever kind of like constraint system you want to use, right? Right. So second approach, and this was, I think, presented last week, so I'm not going to go too deep into it, but basically what you're going to do is you're going to use semi-honest 2PC and then a commit then proof snark, a commit then proof zero knowledge proof. So here you have the commit then proof kind of zero knowledge proof, which is interactive. So you already exploit the possibility that your verifier can hold a secret value. And the general process is kind of like similar to like the previous protocol, but with like a private client verifier. What you end up with is communication that is roughly like 14 times less because like of semi-honest 2PC, and a vastly more fast compute speed for the zero knowledge proofs, which is around 100x, I guess, better. I don't have the exact numbers, but roughly. And also the memory usage is much lower. So you can now run these things in the browser because you operate kind of in a gate by gate paradigm where you can basically, you don't have to prove the whole circuit in one, but you can basically operate it gate by gate and interactively kind of like prove this relation. Right. So yeah, so what you end up with is a protocol that roughly performs like this. So this is from the paper from Pato Labs. So if you run like, for example, the verifier in North America, right, then you're going to obtain a fairly fairly low processing speed because of like the distance end to end from clients to verifier is fairly small, so you don't have like a large round trip time. But if you have like a large distance between those two, then you have a larger round trip time and basically a higher processing requirement for this. Right, now, one last approach that I want to highlight is basically you can change the system requirements, right? So you can say, I'm okay with like less security in this case under certain assumptions, and then I can have like a different system model, and that allows me to kind of like do different things, right? So, for example, what you can do is you can operate like in something called the proxy mode, I guess, that's commonly accepted. Basically what you do is you weaken the network assumptions. So you say, we assume that that the client, so C, cannot mount a man-in-the-middle attack here between the kind of verifier and the server. And then what we just do is we run the verifier as a proxy to the server, and basically route all of the messages, handshake, and request and response through that proxy and let it save it, right? Like this is not of much concern because it's all encrypted at that point. And then afterwards, you just prove correct encryption with like a snark or any kind of like zero knowledge proof protocol that you kind of like deem feasible in this case. The interesting part here is that you can do this because you assume that the server is honest. So whatever the server sends is fine. So you can assume that this response here, encrypted with the secret key of the server, is committing, right? So you kind of like achieve kind of like the similar thing by as like up here, right, where you have like the client commit to the response, but in this case you just like let the verifier act as a proxy and assume that the server response is committing anyways, right? Right. So why is this interesting? So the interesting part here is you obtain something like a TLS oracle that is independent basically of the local situation of the verifier and the client. So you have kind of like constant communication because you have a non-interactive snark here in the last phase where you prove like handshake and encryption. So it doesn't really matter how far you are away of the verifier because like the round trip time itself doesn't like basically have as much impact on your protocol. Right. So there's a bunch of deployments of this. So for example, you have Payload Labs, you have TLS Notary, which is also developed by PSE. They commonly follow this 2PC approach. So this is kind of approximate, right? So don't take it for, and then you have Reclaim, which basically operates in this proxy mode, where you just route everything over it and afterwards prove it with a snark. And there's a bunch of academic works that also outline this. So what is the takeaway here is it's basically by observing the unique requirements of an application, you should also choose kind of like zero knowledge proof that you want to apply, right? Because even for one application, which is kind of the TLS Oracle application, you might end up with different solutions that have different performance properties throughout, right? Like with non-interactivity, interactivity. And some might be more beneficial in some use cases than others, right? So let's now look a bit at the application side and how this is done in practice. So as you can see, there's like a bunch of different, if you look at different applications, people apply vastly different proof systems, I guess. Whereas in blockchain applications, basically everyone focuses on snarks. The simple reason for this is that you need like a short proof verification time and a short proof size in order to verify things on a blockchain, because otherwise it becomes very costly with regards to gas consumption. Whereas kind of like in other applications where you have, for example, let's say, for example, like TLS oracles here, right? You have alternatives with commit and proof snarks, which kind of like optimize commit and proof zero knowledge proofs, which optimize over snarks, or also kind of like proving software exploits. So for example, if you want to prove a software exploit, you don't necessarily need an on-chain prover for this. So you can do this kind of like in an off-chain environment. Let's say I want to prove that like Amazon has a software exploit in some of the code, right? Like I could just send a proof of it to them without disclosing the actual exploit, which is kind of like okay if like Amazon runs a computationally powerful verifier, right? Then I can also use like different protocols that don't have like very succinct verification. Right, but you can see like for some of these snarks are still used, I guess mainly due to the requirement of verifying it on the blockchain. Right, so I mean the ideal thing, like if you think about, for example, the commit then proof approach for TLS oracles, right? Like ideally what you want is you don't only want the verifier in the end to send kind of the signature, right? Like let's say you prove something and then the verifier says like, okay, this is correct with like the commitment that I have. And then I send a signature, which can then be used as a credential, right? Ideally, what you want to have is you want to have kind of the flexibility to say as a client, I just kind of like get this authentic data from server, and then I can kind of like construct zero knowledge proofs or like zero knowledge proofs that are provable by a smart contract afterwards. So how you can do this is you want to kind of have the best thing of both worlds, right? So you want to have very fast execution in this off-chain environment where you have a verifier that verifies your commit then proof snark, commit then proof zero knowledge proof. Then afterwards, you still want to use the data and the kind of like authenticity that you obtained through the TLS oracle to prove some kind of statement to a smart contract that might be flexible afterwards, right? So you want to prove different statements on like a ciphertext that you obtained from some kind of server. So the interesting observation is here that basically all of these different zero knowledge proof protocols work on different types of commitments, right? For example, the Plonk snark works on KCG commitments. The ZKP, the commit then proofs zero knowledge proofs operate over what's called IET-max, information theoretic message authentication codes. What would be cool is if you can just transform commitments, right? So in the TLS Oracle case, you already end up with commitments to all of the things that you want to prove afterwards in the snark anyways. So instead of like the most optimal thing that you can do is kind of like transforming these information theoretic message authentication codes to for example Patterson commitments or some other additively homomorphic commitment that you can then afterwards use with a snark to prove something towards a smart contract, for example. And I think that's really, really interesting, like the composability of these different zero knowledge proofs and how they exploit basically, the kind of environment that you kind of like operate in different protocols, right? Right. So now to the last part, which is basically, do you actually need a zero knowledge proof, right? So I hope this kind of like gave a good intuition of what kind of the trade-offs are and what you can kind of do to like kind of like merge different things. There's been like different works recently that optimize for this. For example, there's been one recent work that outsources basically like that specifically focuses on AES, for example, where you outsource the computationally expensive Boolean arithmetic that you would have to do in a snark. That basically outsources to a lookup protocol, and then afterwards proves basically with a custom lookup argument that is based on like Sigma protocols that IAS encryption is correct. That was like a recent paper, and there's also other papers that, like for example, Lego snark that like combines different snarks with different properties. So I think this composability property, like in different environments, is fairly interesting, even beyond snarks. So yeah. maybe this paper helps a bit in kind of like pushing this a little bit forward. But yeah, now to the interesting question: do you actually need a zero knowledge proof? Sometimes the answer might be no, right? So, for example, if you have an incentive compatible mechanism, right? Let's say you have a witness protection program, right? Like a witness protection program might be, I'm kind of like a witness in some kind of law case or whatever, and I have to be situated in this kind of area, right? Ideally, you kind of like, you as a witness are not incentivized to provide like malicious proofs, right? That you're somewhere outside of this witness protection area, because you want like the people that actually protect you to know that you're still in the area that you should be. So the only thing that you might need it for is actually privacy and not actually authenticity. So you might want to create like a zero knowledge proof of location, right, or something like that. Where you prove that you're actually just in this boundary, but like the actual prover is not really incentivized to provide like non-authentic locations. Similarly, there's other applications without privacy. Let's take, for example, again the TLS Oracle case, right, where you have a client. So this is like the client, right? Like you have a server. And the only thing you really need it for example, if you want to prove that a PayPal payment has been executed correctly, and let's say you're already operating in kind of like this proxy model, right? Like you have like the client, you have the proxy, you have the server, and everything is routed through there. What you can just rely on essentially for ensuring authenticity is OAuth 2.0, right? So let's say you have a PayPal login, you pass the login token to the backend. Let's say this acts as a proxy, right? Then you send the login token to the PayPal API, and you receive some kind of like checkout link, right? And this token is basically restricted in the access scope that it actually has. So you're only permitted to do the actual operation as like the backend operator that you're kind of like constrained to by the client. And then basically the only thing the client has to do is kind of like click on checkout, and you as kind of like backend operator can still verify that this payment has actually been executed by using your access token that has, for example, the read that allows you basically to read whether some transaction has been executed or not, right? So in this case, you probably wouldn't even need a zero knowledge proof. The only reason you would need a zero knowledge proof is for privacy, right? If you don't want the backend to learn your actual identity that you have on PayPal, like your email or something, right? Right. And yeah, maybe finally, when do you need a Snark? I think maybe to kind of like come back to the beginning and why this work was kind of conceived is that we see like a lot of Snark applications and a lot of applications that would probably benefit from like different approaches beyond Snarks. But Snarks are basically used because like there's the best development support, right? Like it's much easier to just bootstrap a prover and run it in the browser than kind of like doing the same thing with like a commit then proof protocol, because like you need to have like very specific domain expertise to actually construct these things in software. So yeah, I think a Snark is really, really beneficial if you either have like a computationally weak verifier, which is the case for a blockchain, which is basically a very slow computer, or if you have many verifiers. Let's say like if you want to prove your location to like 200 peers at one time, right? So yeah, then a Snark can be really beneficial. But I think we see like Snarks applied in applications, that would just benefit from other alternatives as well, just due to the ease of development. And I hope that this paper will kind of, will basically, bring people to think about, how can we develop better tooling for other solutions that might benefit us, and how can we kind of like improve composability of these things to get like the best out of both worlds. Yeah. Great. That's basically it. If you have any questions, I'm happy to take it now. Yeah, thank you very much.
So I do not see any questions yet on the chat, but I have a few myself, so I'll indulge.
Yeah.
So you say just at the end that you do need a stack when you use when you're expecting many verifiers, but I think if I remember well, the first snacks that were produced were about specific designed for specific verifiers. So I'm not sure if they are much cheaper than let's say all-purpose current snarks, but this exists. This also exists.
Sorry, can you what exactly was the question? Can you repeat it?
So you say here, when do you need the stack? And you say when you have many verifiers. My question, what I was pointing at was we also have designated verifier snarks.
Yeah, right. But then you would need to like reprove to all the verifiers, right? Like, because like I guess the nice property of like, let's say you want to like send a proof of your location, right? Like let's say you're somewhere here, and then like you have like 5 or 3 verifiers, right? If you want to use like the designated verifier snark, you would have to execute the protocol with each of them. And you would also have like a larger communication overhead, right? Whereas if you have a snark, you can basically just broadcast your proof to all of them at once, right? Like you can just broadcast your proof non-interactively. Whereas here you would have like basically an individual protocol with each of them. If you use like a trivial interactive kind of like designated verifier zero knowledge proof. I think there's also like threshold designated verifier proofs where basically all of these basically share have a different key share, right? So you have like whatever S1, S2, S3, and then they kind of like do a threshold verification. Yeah, that might also be like a possibility, but if you have like a lot of verifiers, I guess the best thing is to just non-interactively broadcast like a snark proof, right?
Yeah. So yeah, one thing that was quite interesting is you mentioned that snark were composable. So in the blockchain domain, we can see already as Stark plus Snark. You mentioned here MPC in the head or 2PC or others plus Snark, which has its proper advantage. I think in my mind, this is one of the biggest advantage of Snarks, that we have this versatility. So not only there is a composition, which for Snark in that case is mostly about succinctness and fast verifier. But we also have lookup arguments, recursion, and a few and a few other techniques that makes snarks very interesting, especially in the blockchain scenario here for people. So my question is, do you see this happening in the MPC or in the other proofs technologies?
I'm not aware of composability works in the MPC domain, but I'm also not like super deep into it, so I might just not know of them. Yeah, that might be probably the best answer.
Thank you.
Yep, great. With pleasure.
Yeah. So it seems people are either very happy because they have no questions or very shy. So I think we can finish here. So thanks a lot, Jens, for joining us today and for this presentation. It was a pleasure.
Yeah,
and
with pleasure.
For attending. Have a good day.
Thank you for having me. See you. Bye. Thanks.
Bye.